So, let us have some interactive problem solving sessions by students who have taken this course. So, you will see some illustrations and examples into problem solving which is useful to understand and digest the concepts learnt during the lectures. So, this problem was posted as part of homework 3 in mathematical methods and techniques for signal processing in 2016. So, this is a sort of a practical problem which requires theoretical justification. So, here is the situation. A student performs circular convolution instead of the usual linear convolution when filtering sequences using a dyadic wavelet filter bank. Assuming that all other operations are the same and the filters are normalized to unit energy, does Parseval's energy conservation hold? Justify mathematically. So, you have learned linear convolution and circular convolution. Somebody wants to experiment with circular convolutions from linear convolution, and there are some advantages of doing circular convolution, because if you do linear convolution, every time the sequences at the output go with increasing length because of the convolution process. So, somebody tried this experiment, and you want to check if this result is correct, right. So, we take a signal x of n, we filter it through a low pass filter which is 1 plus a delay upon root 2. This is to ensure that the energy is normalized to unity. So, it goes through a low pass filter here and a high pass filter followed by downsamplers which is downsampling by 2, and then again in the low pass band it goes through a low pass and a high pass followed by downsamplers, and this is the process in the analysis bank, and we would like to investigate if Parseval's energy conservation property is satisfied under circular convolution when you do the filtering operations.
Okay, hello all, I am Chaitanya, a PhD student at IIC. I am going to discuss the problem that professor has mentioned. So, here we have an analysis bank where we are doing a dyadic decomposition. Here the low pass and high pass filters are basically based on the Haar discrete time Haar wavelets that we have studied in the class. So, instead the twist here is these filters whatever we are seeing, they do not do a linear convolution that we have studied in the class, instead it is a circular convolution. So, before solving into this, I will introduce you to the concepts of circular convolution. So, for this circular convolution, let us say we have two signals. So, typically, so this is like a transmitted signal x of t, let us say it has a duration of up to a length L, and we want to convolve it with another signal, typically a filter response, let us say h of t. So, let us say it is given by this with some duration let us say t. So, now typically you know the linear convolution operation, how it is done. So, what we do is for the linear convolution which is times h of t. So, what we do is we take the signal x of t and we take the reflection of the other signal which is h of minus t. So, which would look something like this, and what we do is we overlap this particular h of minus t at different shifts with respect to h of t, with respect to x of t, and then add it, multiply and add it. So, essentially for example with some shift T1, let us say we call it as T1. So, if we want to get the convolution output at T1, so what we do is we overlap this reversed filter response in this particular fashion, multiply the two signals and then add that, sum it up or integrate for a continuous time signal. So, that way we will get the result of convolution at shift T1. Similarly, for any arbitrary shift T2, so we overlap at that particular arbitrary shift T2 and then multiply these two signals and then add them. And for looking at on the shift T3, so we do the same thing again. So, this is how we do a linear convolution. So, essentially we have x of t, the convolution x of t convolved with h of t is nothing but here in this particular case integral over tau x of tau times h of t minus tau d tau. So, this is essentially the regular convolution that we have. So, what happens with circular convolution is slightly different. So, I will illustrate it with the same example on how we do the circular convolution. So, let us say I represent the circular convolution using the convolution symbol with a circle around it, h of t. So, now so we have this signal x of t. So, when we are performing this circular convolution, what we do is see this translate at time t1. So, in this particular case what we do is we take the same filter response t1. So, till the signal x1 is present, within the limits of the signal x1 we multiply the same signal t1, but wherever it is going beyond the limits of the x1 signal, we wrap it back from the end. So, it goes back like this to the end, and now we multiply these two and add it. So, this is the circular convolution. So, if we are looking at a signal somewhere in middle, it is not going to be different from the linear convolution. But let us say if I look at another shift T3 like we have seen here. So, let us say T3, in order to avoid confusion I will just put the this shifted version here. So, till this particular point it is the we actually make the product, but this particular part of the signal is not overlapping with x1. So, what we do is we instead take this particular part back to the beginning of the signal, and then multiply these two signals and do and add them up. So, this is essentially the idea of a circular convolution. So, here another thing that we can see is this is same as repeating this particular x of t signal periodically at intervals L, and performing same linear convolution operation. So, if you look at the shift T1, so this blue response is overlapping with the replicated original signal x1. So, this is somewhat similar to doing a linear convolution operation when the signal is repeated. So, this is essentially the circular convolution. So, more fundamentally if we look at a discrete time response. So, let us look at what happens when we do x of n circular convolved with let us say delta of n minus 1. So, in this particular case what happens is we have x of n. So, it might have some impulse responses. So, this is a discrete time signal and we have delta of n minus 1. So, what happens here is when we multiply these two signals. So, at time shifts so here we have time shift 0, 1, 2, 3. So, these are the values of x of n at different time different time instances. So, now when we look at different time so now if we reflect this signal back, so delta of minus n minus 1. So, it is going to be at minus 1. So, now if we at time shift, so now what we are going to do is perform this circular convolution operation. So, we take this particular reflected signal delta of minus n minus 1 multiply with x of n. So, here with time shift 0 it is not overlapping with x of n. So, hence we wrap it back to time instant this delta this pulse will be wrapped back to this particular instant t equal to 3. So, what happens is this is what we get. So, let us say these values are x 0, x 1, x 2 and x 3. So, the resultant signal is going to look like this. So, this here you have x 3, x 0, x 1 and x 2. So, essentially what we have seen is when we are delaying the signal, it has wrapped around. So, for a linear convolution operation, when we delay the signal, it is a linear shift in time. Here what we have seen is a circular shift in time. So, a delay corresponds to a circular shift, not the linear shift. So, that is the fundamental idea of a circular convolution operation. So, just like how we have derived this one. So, we know that x of n convolved with h of n is sum over m h of n minus m or equivalently it can be written the other way as well. You take h of m times x of n minus m. So, a similar result can be proven here. So, what we have seen here is, so from here what we have is x of n circularly convolved with a delta function n minus 1 is essentially a circular shift. Shift of x of n minus 1 . So, now this gives us what a circular convolution is. So, now we use this property of circular convolution to look into the problem. So, for this particular problem we have the input signal x of n. Let us say it goes from 0, 1, 2, so on till L minus 1. So, it has L non-zero values, or the duration of the signal is L. So, let us say these values are x 0 to x 1, x 2, so until x L minus 1. Now, the idea is as follows. So, essentially x of n convolved with, or circularly convolved with 1 minus z power minus 1 by root 2 is nothing but x of n by root 2 plus minus 1 by root 2 times x of n circularly convolved with delta of n minus 1. So, in this case we have this as x of n. Now, what will be x of n circularly convolved with delta of n minus 1? So, it is going to be circularly shifted signal. So, here we will have x of L minus 1, here we will have x naught, x 2, it will, and the final value this x 0 will come back here at dimensions L minus 1. So, this is what we have. So, this one is y 1 of n, and similarly y 2 of n is nothing but x of n by root 2 plus 1 by root 2 times x of n convolved with delta of n minus 1. Yeah. So, now from essentially what we y of n can be obtained by subtracting these two signals x of n and these two signals and scaling by root 2, and y 2 of n can be obtained by adding these two signals and scaling by root 2. So, that way the values that we have here y 1 of n will be x naught minus x L minus 1 by root 2, at dimensions 1 it is going to be x 1 minus x naught by root 2. Here, yeah, there is a typo. So, this is x 1 . So, here we have x 2 minus x 1 by root 2, and the last one is going to be x L minus 1 minus x naught by root 2. Similarly, we have y 2 of n is instead of these negative signs we will just have the addition signs. So, here we have x naught plus x L minus 1 by root 2, x 1 plus x naught by root 2, x 2 plus x 1 by root 2, and the last one is going to be plus x naught by root 2. So,
The last one XL minus 2 or X naught.
okay, yeah, thank you. So, yeah, there is a typo here. Yeah, when we do the circular shift, here we will get XL minus 2. So, these things also will change, XL minus 2, XL minus 2. So, now we have this y1 and y2, we are going to downsample by 2. So, essentially we are going to discard every alternate element. So, if we look at y1 tilde of n, we will retain these samples x1 minus xl minus 1 by root 2. So, this is kept, we have x2 minus x1 by root 2, and every alternate things are skipped, and the last one that will be left here would be either xl minus 1 minus xl minus 2 by root 2. This if L L is odd, and or the previous one, which is xl minus 2 minus xl minus 3 by root 2 if L is even. And y2 tilde of n similarly is going to be the same set of samples with just the positive sign. So, now these are the outputs after the first stage of decomposition, and now we have to compute the energy at, of these two signals at the output. So, for that essentially what we are trying to prove here is yeah. So, a small correction. So, these values are plus so we have the outputs at the first stage of decomposition, and to prove the Parseval's theorem, so what we need to prove here is summation of all these y1 tilde of n square plus y2 tilde of n whole square summation of n. This should be same as summation over n x of n whole square. So, this is essentially what we are trying to prove. So, we will use these properties. So, here we see that y1 tilde of n and y2 tilde of n are of the form a minus b and a plus b. So, we know that a minus b whole square plus a plus b whole square is 2 times a square plus 2 times b square. So, I mean using this we can compute this y1 tilde of n square plus y2 tilde of n square. So, the values that we have we will get right now for y1 tilde of n whole square plus y2 tilde of n whole square. So, the values that we will get from the previous slide. So, we here for the first term we have x naught square plus xl minus 1 whole square, and because of the factor 2 here this root 2, the contribution of this root 2 will get cancelled out. So, you will have x naught square plus xl minus 1 square, and the next term is going to be x2 square plus x1 square, and the next term is going to be x4 square plus x3 square, and the last term depending on whether L. So, here we have two cases, whether L is odd or even. So, depending on the case that we have, it will be x L minus 1 whole square plus L minus 2 whole square if L is odd to odd, and for L equal to even, the final value it is going to be different. It is based on it has contributions of x L minus 2 and x L minus 3. So, we have x L minus 2 whole square plus x L minus 3 whole square for L even. Now, we have these terms. So, to get the energy at the output of first stage, we just need to add all these terms. So, for which so adding all these terms, so again depending on whether L is odd or even, we will have two cases. So, if we look at L odd case, so x1 appears only once, x0 appears only once, x1 appears once, x2 appears only once, x3 appears only once, x4 appears only once, xl minus 2 also appears once. However, xl minus 1 appears twice. So, here the output is going to be xl minus 1 whole square plus summation n equal to 0 to L x L whole square, and when L is odd. When L is even, you see that this repetition of x L minus 1 does not happen, and each individual term x0 till x L minus 1 they appear only once. So, essentially the output is going to be 0 x n whole square, L is even. So, from here so this is energy at the input, and this is the output energy output energy. And for L equal to even, so we have energy conserved, and for L equal to odd, energy is not conserved. Now, so here we have done this for the first stage. Now, what happens at the output of second stage? So, essentially we have that for first stage L must be even, for energy conservation. Now, let us see how many samples we have after the first stage. So, if we for L equal to even, so here we have x0, x2, x4, so on till x L minus 2. So, for L even we have L minus 2 by 2 samples at output. Sorry, it is going to be L minus 2 plus 1 samples at output equal to L by 2 right, output. So, if we want energy conservation, so basically for second stage, if we want energy conservation, L by 2 must be even, that is L multiple of 2 square for let us say I call it as energy conservation for energy conservation. So, for similarly if we extend to kth stage, so L is multiple of 2 power k implies energy conservation. So, in summary, we have looked into this circular convolution operation. This circular convolution operation is typically done on finite duration signals, as you can see here. So, for infinite duration signals, there is no concept of wrapping it around to the end or to the front. So, circular convolution is usually done for finite duration signals, where the delay here is a circular delay, not the linear shift. And we use this circular convolution to analyze the energy conservation principle for the particular structure that was given. And we see that only when the length of the signal satisfies some certain properties, we see that the energy conservation holds true.